So as we've already seen in our examples from the last couple of lessons, the most useful double displacement reactions are precipitation reactions. Okay, so where you form a solid product out of soluble reactants. However, as we saw previously, in order to ensure that a reaction actually takes place, you're going to have to be able to identify which ionic compounds are soluble and which ionic compounds are insoluble, because it's only the insoluble compounds that will form a precipitate. Okay, so in order to do this involves knowing some solubility rules. Okay, so this is your textbook's list of solubility rules. And what you have to do here, we're going to go through several examples, but you have to apply these rules in order. Okay, so you start with rule 1, then rule 2, then rule 3, etc. And if a rule doesn't apply to any of the chemicals in a particular compound, you just skip down to the next one. But then you'll eventually get to the point where you've either concluded that a particular compound is soluble or you have concluded that it's insoluble. Okay, so let's go over these rules quickly. So first of all, alkali metal salts, lithium, sodium, potassium, whenever they're present, anything containing them is going to be soluble. That's really, really important. You're going to see a lot of sodiums and potassiums. And then also going into this category, although they're not alkali metals, are ammonium salts. Do you remember ammonium is NH4+. It's one of the few polyatomic ions that you learned that actually has a positive charge. It's a polyatomic cation. So again, if you have ammonium anything, it's going to be soluble. Those are cations, rule 1. Rule 2, anions. Nitrates, acetates, perchlorates are soluble. Okay, so then rule 3, going to cations again, but now we're getting products that are metals. Silver, lead, and mercury salts are insoluble. And then rule 4, back to anions. Chlorides, bromides, and iodides, those are from group 17 on the periodic table, also known as the halogens. They are going to be soluble. Okay, and then rules 5 and 6 get into some others of the polyatomic anions. Okay, so carbonates, chromates, sulfides, oxides, phosphates, hydroxides, most of them are insoluble. I wouldn't even worry about this exception. It's probably not even going to show up. And then sulfates, most of them are soluble except for 3 of the examples from group 2 from the alkaline earth metals: calcium, strontium, and barium, the 3 lower ones. Magnesium sulfate is actually soluble. Okay, so as an example, let's consider a reaction. So in this case, we're going to consider the reaction of copper nitrate with sodium hydroxide. Okay, and the products here are copper hydroxide and sodium nitrate. So you have to, I have intentionally excluded the states of the products, and you have to answer the question, is this a precipitation reaction? And based on what we saw previously, is this a reaction at all? So what that really means is, can we write solid next to one of the 2 products? And in order to do that, we have to conclude that one of these 2 products is insoluble. Okay, so how we crack it? We look at the solubility rules, which I've reproduced again, and apply them to each product until you get one that is insoluble. Okay, so let's start by looking at copper hydroxide. Okay, copper, it's not an alkali metal or ammonium. Hydroxide is our anion. It's not a nitrate, acetate, perchlorate. It's not silver, lead, mercury, chloride, bromide, or iodide. So rules 1 through 4 do not apply to this. But then we get to rule 5. It is a hydroxide, has OH there. So our rule 5 is telling us, if we haven't already excluded that hydroxide from rule 1, that hydroxides are going to be insoluble. So based on rule 5, we're going to conclude that copper hydroxide is insoluble. Now, what about sodium nitrate? Well, we've already found the one that's insoluble, so the answer already is yes, that it's a precipitation reaction. But let's go through this analysis for sodium nitrate. Alkali metal salts, rule 1, are soluble. Sodium is an alkali metal, so sodium nitrate is going to be soluble, and you don't need to go any further. Okay, so adding states to this reaction, we stick a solid next to copper hydroxide and an AQ next to sodium nitrate. So yes, it is a precipitation reaction. Okay, and just for a little more practice with the solubility rules, you don't have to do this when you're solving this particular problem, but let's just go through these solubility rules and apply them to the reactants because there are a couple more chemicals that we have on this slide. So what about copper nitrate? Well, rule 1 does not apply because the cation is not from group 1, but group 2 nitrates are soluble, so therefore it is soluble by rule 2. Sodium hydroxide is soluble by rule 1. Okay, alkali metal, sodium. Anytime you see sodium, it's always, always, always going to be soluble. So this is why you need to apply the rules in order. Otherwise, you may get down to rule 5, look at that first, and conclude that sodium hydroxide is insoluble. But you have probably already in lab used an aqueous solution of sodium hydroxide. It most certainly is soluble. Okay, so then what I want to move to is a slightly more difficult problem, and that is giving you just the reactants and asking you to predict the products. Okay, so what I want you to do, we're going to consider the reaction of silver nitrate with potassium chromate. That's what CrO4 is. So I want you to fill in states for both of the reactants, write the products, including the states, and then balance the equation. Okay, so let's get to it. So first of all, if you see a problem like this again is kind of prep work for solving the problem, but I want you to make sure that you know which ions are present in the reactants. Okay, so you need to know that silver nitrate is giving you Ag plus and NO3 minus. You need to know that potassium chromate is giving you K plus and CrO4 2 minus. Okay, so you have to, again, chromate is one of those polyatomic ions, and this one is a 2 minus, and that's why in the chemical formula there's 2 K pluses. Okay, so then what you want to do, since this is an exchange reaction, is you want to switch the partners to get potential products. Okay, so you got to make sure now we're going to pair up silver with chromate and potassium with nitrate, but you got to make sure that we include 2 silver cations because silver forms +1 ions in order to balance out that 2 minus chromate ion. Okay, so now we're going to use the solubility rules to assign states to each compound. Okay, so we're starting out with the reactants because you have to fill in the states for the reactants. By rule 2, we have a nitrate, so therefore silver nitrate is going to be soluble. We can write an AQ next to it. And then for potassium chromate, by rule 1, that's going to be soluble because it contains potassium, which is an alkali metal salt. So yes, I mean, you'll have a periodic table in the exam, but you have to start to get some familiarity as to where some of these things you're going to see over and over again are on the periodic table. And then moving on to look at the products, potassium nitrate is also soluble by rule 1. Yes, it would be soluble by rule 2 also, it's a nitrate, but remember we get to rule 1 before we get to rule 2. Then finally, silver chromate is going to be insoluble by both rules 3 and 5. It's a silver salt and it's a chromate salt. Okay, so it's going to get a solid next to it. Okay, so silver nitrate aqueous plus potassium chromate aqueous gives you silver chromate solid plus potassium nitrate aqueous. And I have a picture of this reaction taking place also. Potassium chromate is interesting in that it is actually a yellow compound. You will actually find that many compounds involving the transition metals are colored. Silver nitrate, or at least the ones through group 10, not so much 11 and 12. Silver nitrate is a clear and colorless solution, but when you take the yellow potassium chromate and drop it into the clear and colorless silver nitrate, you get a deep red precipitate of solid silver chromate. The last thing we need to do is balance the equation. Okay, so we start out by, or at least I will start out by balancing silver. Okay, so on the left-hand side of the equation, there is 1 silver nitrate. On the right-hand side of the equation, there are 2 silvers in the silver chromate. So therefore, I'm going to write a 2 in front of the silver. And then the next thing I'm going to do is I'm going to balance out potassiums. Okay, so potassium shows up on the left-hand side. There's 2 potassiums in potassium chromate. There is 1 potassium in potassium nitrate. So therefore, we have to put a 2 in front of the nitrate, in front of the potassium nitrate on the right-hand side of the equation. Okay, so then nitrogen is going to appear once on each side. It's actually fine because we've made 2 nitrates on the left, 2 nitrates on the right. And we can actually keep all of our polyatomics together when we're balancing. We don't technically have to consider everything atom by atom because all of the nitrogen is in the nitrates and the oxygen is in either the nitrates or the chromates, and those are staying intact. Okay, so there's 1 chromium on the left, 1 chromium on the right, 7 oxygens on the left, 7 oxygens on the right, so those are both balanced. Therefore, simply putting the 2 in front of the silver nitrate and the 2 in front of the potassium nitrate on the right successfully balances this equation. Okay, so now I think you now have the tools you need to be able to crack precipitation reactions. And at this point, you just are going to need some more practice on them. As we move forward in the material in these lessons, we're now going to switch gears a little bit and start talking about acid-base reactions, which is the other major class of exchange reactions that you're going to have to become familiar with.